us. All right. So the quiz on Monday is the plan right now. And so like I said, section 4 is where we learned about this idea of global max min and the chart stuff. And now, as that relates in section 4, we did it with polynomials, right? With cubic, we did some examples of a cubic and where's its max and min and that kind of stuff. And then yesterday we did number 37, which was trig, knowing the trig stuff. And even if you have trouble with the no calculator trig values, you know, you still can get a lot of points in a global max min problem. If you do the derivative, set it equal to 0, and you can't get the cosine equals -1/2 at 4 pi thirds and 2 pi thirds, if you have trouble getting that, you get 5 pi 6 and 7 pi 6 or something like that. Keep going with the problem, because all the rest, once you get the wrong stationary points, everything else after that will be wrong. But you won't lose all those points. Even if you have the wrong stationary points, if you go ahead and do a proper number line, and you plug numbers in, and you find intervals of increasing and decreasing and local max min, they're all wrong, but that's good stuff that you're doing, just with wrong numbers. So you can still get some of those points. Okay, so keep that in mind. Then we also, in the next couple days, have calculator ones to do, which basically the difference on the calculator ones means when you get to the part where you're going to set the derivative equal to 0, instead of solving it by hand algebraically or knowing the trig values, you'll go to your calculator, menu, algebra, solve, and let the calculator solve it for you. But there are some issues there, especially with the trig ones, on how to get the calculator to solve it right for you. So we do have to do that. So we'll be doing that with the calculators a little bit tomorrow. But on the quiz, half of the points, you know, out of 35 points, 18 to 20 will be on that chart and global max min, like that number 37, that gigantic problem we did yesterday, right, with all that stuff in it, the number lines and the list of candidates. That's a big part. Half the points are in problems doing that. Okay, so that'll be, now there wasn't any of that on your homework today, and on your homework tomorrow there is some of it again. Okay, so we're practicing that and get to do those. Okay, so that's a big deal. Today's homework was mostly about derivative rules and antiderivative rules. And antiderivatives and the derivative rules will be I don't know, 15%, 20%. That might be about 8 points of the 40 points that we have, maybe 20%, whatever. Okay, so that there'll be some of those on there. Okay, and then the rest, maybe 12, 15 point, 12, 13 points, something like that, will be in the differential equations, which is the new thing we're going to talk about today. Okay, differential equations. And that's basically the things that will be on the quiz. Okay, now, all of those things involve the derivative rules, or the max min involves some trig functions, sine, cosine, involves logs or exponentials, or could involve just algebra with factoring and stuff like that. Okay, so that's kind of a summary of the things that we need to be able to do. All right, so let's go over this idea of differential equation. Okay, so for your notes. Okay, first of all, definition. A differential equation is an equation that involves one or more derivatives. An equation that involves one or more derivatives. Now, so what's that mean? What's an equation? Well, an equation is basically anything with an equal sign in it. Okay? So, if you have, you have 3x plus 5 equals 17. I mean, that's an equation. It's got an equal sign in it. It's an equation. So if it's got an equation, if it's got an equal sign and it's got a y prime in it, now we will, in difference equations, we use y as our output more than like f of x, and sometimes they're not even functions. Okay, so our output variable will be y, and our input variable on differential equations is usually t, because they involve time a lot, but it could be x. Okay, but our output variable is usually y. So if it has a y prime or a y double prime in it, and it's got an equal sign in it, it's a differential equation. So we've actually already done some differential equations today when you were doing antiderivatives, right? I mean, essentially you had a derivative and then you did the antiderivative of it to get a function. We'll talk about that here in a minute. So that's what a differential equation is, all right? The next thing I would say about a differential equation is the solution to a, and then your book uses the acronym DE for differential equation a lot, so okay. The solution to a DE, a differential equation, is the original function, parentheses, y. In other words, we have to, see, we've got to differentiate here between an algebra equation, which you're used to seeing, and a differential equation. An algebra equation would be like 3x plus 5 equals 17. Now, what's the solution to that? A number, in this case, 4, right? So the algebra equations you're used to doing in Algebra 1 and Algebra 2 are all courses mostly about solving different types of algebra equations. And the solution is a number. And so we use the word answer a lot. Find the answer. Well, what's that mean? Answer can mean a lot of different things. Okay? The solution to an algebraic equation is a number or numbers, right? A quadratic might have 2 solutions. Or you might have multiple solutions to an equation, right? But it's always a number. Differential equation, so we got to kind of get out of that mindset. The solution to a differential equation is the original function y. So it's like y equals with x's or t's in it, but without any derivatives in it. If it's got derivatives in it, it's a differential equation. The solution to that is the original function y that makes that differential equation true. See? The reason 4 is the solution to this is because it makes it true. If I put a 4 in here, I get 17 equals 17, which is a true statement. If I put any other number in for x, I get a false statement. So that's what a solution is a thing that you plug in to make a true statement. So that's what we are going to have here. Now, there are 3 categories, for this class anyway, there are 3 categories of differential equations. Okay, this is just kind of how I categorize them. Actually, there's a lot of different types, like quadratic equations, linear equations, those kind of things. There's a lot of different differential equation types, and they have names. If you are going to be an engineer and have to take Calc 1, Calc 2, Calc 3, usually the class you take after Calc 3 is differential equations. Take a whole class of differential equations solving, just like Algebra 1 and Algebra 2 are courses in solving algebra equations. Differential equations, of course, in solving different types of differential equations. Now, in your book on page 122, just to read a little bit right at the beginning, it says algebra equations describe relations among varying quantities or amounts. So like Pythagorean theorem, a squared plus b squared equals c squared, that says how the lengths of the sides of a right triangle relate to each other. And that's what algebra equations do. They tell how different variables relate to one another, different amounts. Well, if you remember when we first learned about derivatives, we talked about f being an amount function, like miles, or dollars, like the cost of a book. And then x might be how many books you have, or x might be how many hours you travel. And that would be an amount function, f. And then f prime was what? The rates, the slopes of the amount function. So it's the rate that those amounts are changing, like your miles per hour, or your dollars per book, or that kind of thing. Okay, so we had amount function, had rate function. Well, that's what differential equations do. Since they have derivatives in them, they involve rates. So differential equations take and not only relate the amounts of some variables, but the rates at which those amounts are changing. Okay? the rates that those amounts are changing. So, they have a comment there, they say nature's voice is mathematics, its language is differential equations. Okay, because differential equations, we can describe many, this is why it's so important like in engineering, we can describe many things in the physical world with differential equations because it involves the amount, the quantity, and the rate that those quantities are changing. All right, well here's the three categories. One is those that can be solved with basic antiderivative. Those that can be solved with basic antiderivatives. All right, let's do a couple of simple examples here. One would be y prime equals 3. Now, do you see why that's a differential equation? It's got the two things you need to be a differential equation. What are they? Equal sign and a derivative, right? It's got a y prime in it, and it's got an equal sign. It's an equation that's got a derivative in it. It's a differential equation. Okay? So the solution to that differential equation is going to be the original function y with just x's or t's in it. Now again, most of the time our differential equations use t as the input variable because most of the things that involve rates involve time. So we'll use t a lot. If you accidentally use x, sometimes not a big deal. If you go on your calculator, you know when you do a graph, you got to use x as your variable, input variable. When you go into differential equation mode on your calculator, you have to use t as the input variable. Okay. So what would this be? To go from y prime to y, that's an antiderivative, right? So what's the antiderivative of 3? 3t. Now, we haven't went over the homework today, but that would be the antiderivative. Why? Because a derivative of 3t is 3. Anytime you do an antiderivative, and this is something we'll talk about when we go over the homework, when you do an antiderivative, it's really kind of guess and check. We have derivative rules that we follow. But an antiderivative is just like, okay, what would that function have been? So when I do the derivative of it, it checks to give me that. And so here we would just check this. We'd say, oh, the derivative of 3t would just be 3. So yeah, that must be it. That must be the antiderivative. And then we always have to add on what? Plus some constant, because there could have been a 7 there or a 6, and when we did the derivative, it would have been 0. So it would have disappeared. Okay? So this is the solution to that differential equation. So again, we got to get out of that mindset of a solution being a number. The solution is the original function that makes this be true. Now, why is it true? Because if I do the derivative of this, then take this solution, do the derivative, I get y prime equals 3. Yeah, I would get 3 equals 3 because y prime is 3, and so there it is. Here would be another example. Y prime equals 6x minus 5. That is a differential equation, right? It's an equation, it's got a derivative in it. What's the solution? Well, it's the original function y, so that would be what? 3x to the second. Why? Because if you did the derivative of that, it would give you 6x minus 5x. I'm using x. Now, in this one, we would use x because the differential equation was given to me with x as its input variable. So I'll go ahead and use x. And then plus some constant c, right? And again, why is that the antiderivative? Because if I do the derivative, it's 6x minus 5, which is that. So those are just simple differential. So in other words, on the homework today, when you did antiderivatives, you were solving differential equations and didn't even know, right? You were solving differential equations but didn't know that's what you were doing. You were just finding an antiderivative. So some differential equations we can just solve. We can find the original function by just doing a basic antiderivative. Now, the reason we could do those is because they had the input variable over here, we had y prime over here, right? And nothing weird, nothing else was wrong. It's the kind of stuff we've been noticing. But we could have some other ones, and so that's type 2 here. Type 2 differential equations are those that we can't solve yet. Put that in parentheses. But we will memorize the solution. Now, there are going to be two of those, and we're just going to talk about one today. Okay? So, one we can't solve, and we will just memorize the solution. So, the one we're going to talk about is y prime equals k, which is just some number, times y. Now, how is this one different than the ones in type 1? This one has an x or no variable. This one has a y. That's a huge difference. I mean, because y is the output variable. If you get, and the reason we know y is the output variable because we have y prime, right? We always do the prime on the output variable, like f prime, right? Or f double prime. That's our output variable. And so, if we have the, because really another way of writing y prime is dy dx. Remember we talked about that, dy dx or dy dt. In this case, it might be dy dt because t might be the input variable. We don't really know. We don't know what the input variable is here. It doesn't tell us. We know the output variable is y. We can't just do like a power rule. We can't raise this up to a y squared. That doesn't work. That only works when it's the input variable, right? All the derivative rules we have are with respect to x, the input variable, okay? So when we have just x's or just t's or whatever our input variable is in the differential equation, then we can just do a basic antiderivative. But if we have y's in there, if we have the output variable in there, that's weird. We haven't seen something like that before. Okay? But this is a very famous differential equation. Okay? Let's think about what it's saying. Let's say in this case, let's say y was money, dollars, that we put in the bank for a number of years. So y is dollars. What's y prime? Units. Well, okay, you're on to something, but it wouldn't be dollars per year, right? I mean, right? When we first learned about derivatives, that's what we said, the rates, right? So if y here is dollars, then y prime has to be dollars per year, which would be like interest, right? It would be the rate of increase of our dollars, right? That's what y prime would be, the rate of change of the dollars that are sitting in the bank. Now, we talked about this in one of the appendix problems early in the year. This is like direct proportion that you get in science. The way you would read this sentence right here is you'd say the rate, y prime, the rate of dollars per year is proportional to the amount of dollars. In other words, the rate that your money grows is proportional to how much money you have. Now, doesn't that make sense? The more money you have, the faster it would grow. Now, somebody in the other class was asked about percent. If I have $100 in the bank and get 6% interest, and somebody else has $1 million in the bank and gets 6% interest, we're both getting 6% interest. So you might say we're both getting the same rate. Well, we're both getting the same interest rate. But whose money's growing more dollars per year? The $1 million, clearly, right? So it's growing at a faster rate. All right? So basically what this is saying is the more you have, the faster it grows. Now, this would also describe, so this describes compound interest, for example. This would also describe like half-lives, like exponential decay, like of dinosaur bones, right? If y is the kilograms of dinosaur bone, y prime would be the rate of its decrease, right? And so the more dinosaur bone present, the faster it's decaying, right? That's like half-life. So over so many years, you lose half of it. After so many years, you lose the next half. Well, the next half that you lose is less than the first half that you lost, right? I mean, so the amount in kilograms per year or whatever is going down. So it's slowing down the decay, the rate of decay. So this, like I said, this is a pretty simple, right? But it does describe that situation. Here's the solution to it. Not surprisingly, since we were just talking about it, the solution to that differential equation is y equals ae to the kt, the old compound interest formula. You probably remember that from trig last year. Or the PERT formula, I think some of the books use The A was P, like for principal, the original amount you had, and R was, K was like the interest rate. Okay, so this K here, this number out in front of the Y here is the same K that's in there. And then A is just some constant depending on your initial condition, like how much money you put in, whether it's $100 or $1 million, right? That would determine the A value. But that's the solution. We don't know how you could get from here to here. It's definitely not an antiderivative, right? We'll learn that later on. But so right now we'll just memorize that. If you see a differential equation that says y prime equals 3y, you have to recognize that as, oh, hey, that's that special one. That would be y equals ae to the 3t would be the solution. And then we can just work with it. Then we can just plug in. They say, well, how much money do you have after 10 years? And so you put a 10 in for t and you work it out. That's how much you have. So once we know the solution to the difference equation, we can then work with it just like a normal problem. Okay? So that's that type. And then the third type, those we can't solve, period. Now, this year, we can't solve it. If you take a class of differential equations someday, you'd be able to solve it. But an example might look like this. Y prime plus 2x equals 3y, y double prime minus 7. Or something like that. It's a differential equation. It's an equation. It's got derivatives in it. It's a differential equation. What would be the original y equation that would solve that would make that be true? Who knows? Okay, maybe it's no solution, whatever. And we won't even mess with those very much other than to do something we're going to talk about in a minute, which would be verify that something is a solution. Okay? But we won't solve it, you know. And in some of the problems we do on differential equations, they'll actually just tell you in the problem what the solution is. They'll just say, hey, this problem can be modeled by this differential equation. The solution to that differential equation is this. And then they'll ask you questions using that solution. Okay? So the only ones we'll really solve ourselves will be these basic antiderivative, which are some things you already did in your homework today. Okay? Hardest part of differential equations is just kind of wrapping your head around the whole concept of this versus an algebraic equation. Okay, last thing I want to do here, and then we'll talk about the homework, is what I was just mentioning there about verifying something's a solution. Okay, verifying a solution to a differential equation. All right? So it might look like this. Matter of fact, several of your homework problems are going to work with this very same differential equation. So we're given y prime equals 1 over 2y. Now that is not one we can solve. Why not? It's got a y in it. It's got the output variable, right? If that was 1 over 2x, we could write that as x to the negative 1. We could do a power rule, right? Do an antiderivative kind of thing if that was an x down there. But since it's a y down there, we can't do anything with that. Antiderivative y, right? So this would be type 3. We don't know how to solve it. And it's certainly not the one we memorized. It doesn't look like that because it's 1 over 2y. So it doesn't fit number 2, doesn't fit number 1. So this is one of those like number 3. All right? So what we're going to say is, the question is going to be, is y equals square root of x plus c a solution? That's the question. Right? Remember, a solution to the differential equation is the original function y. So is that function y equals that a solution to that? So now let me take you back to algebra here a little bit. So pretend you're in my Algebra 1B class right now. And we got this equation right here. Now these guys can solve this, okay? So let's go back to 6th grade, okay? Got 3x plus 5 equals 17. And we don't know how to solve that. We don't know how to find what x is. We could try a bunch of stuff, right? See, and what would that mean to try it? Guess and check, but you would do what? What do you mean guess what? What would you guess? Number. You guess numbers, you plug it in where the x is, and you see if it equaled 17. And actually, I should make this even a little tougher. Let's make it let's make it a little tougher. Yeah, let's put the plus x there. That always made it tougher then, right? Because now we don't know that it equals 17, right? So now if we try plugging numbers in, what's it end up being? It ends up being 6. Now, why is it 6? Well, because if you plug a 6 in here, you get 12, or excuse me, you get 18 plus 5 is 23. And on this side, you get 17 plus 6, which is 23, right? Now, if I was teaching a 6th grade class or 7th grade class about this topic, what we would say is we'd say this. Well, the question would be more like this. Instead of making them guess a bunch of stuff, x equals 6, a solution. Right? That would be the question. So that's very much like what we've done. I've given you an equation that you don't know how to solve, and I've given you something that I'm telling you I think might be a solution. And I want you to verify that it is. So that's very much like this question. So is x equals 6 a solution? So what I would teach them is I call this a T-chart, okay, with an equal sign. I always put the, go like this and put that line right down where the equal sign is. And what we're trying to do is show that this side is equal to this side. So I'm going to put a 6 in there, and I get 3 times 6 plus 5, and I always make them show their work a little bit. You guys will be showing some work too. And that equals 23, right? And on this side, I get 17 plus 6, which is 23, and then we draw a line, we say, check. It is a solution. If they would have come out different, we just said it's not a solution, right? That's what you're going to do. So let's do that with this problem. So we're going to come over to here, and it's always weird because we got 2 equations, so which one do I do the T-chart on? You just think back to this algebra example. You always take your solution and plug it into the equation. So we're going to take this and plug it over here. So I'm going to put down my little T-chart here. Okay? And what am I going to plug in? Well, in place of the y, I'm going to put this. So I'm going to have 1 over 2 square root of x plus c. Right? That's what I'll have on the right side. What do I have on the left side? Y prime. How do I know what y prime is? Well, we know what y is. So let's do the derivative of this, right? Well, first thing we might want to do is write that as x plus c to the 1/2, right? And let's do the derivative of that. So we know y prime is going to be what? 1/2. We always leave the inside alone. Do we have to kick anything out? Because we weren't multiplying anything in there, right? So we don't have to kick anything out. So that would be y prime. So that would go on this side. Now, are those two the same? Well, we can make them be the same. They are, I think. But they certainly don't. If I ask a 7th grader, they wouldn't think they're the same, right? Just like somebody might not know that that's the same as that. I want it to look exactly alike. So I need to do a little rearranging with algebra. I can either rearrange this one or rearrange this one. Doesn't matter. How about we move this one to the bottom with that negative power? So that'd be 1 over 2 x plus c to the 1/2. And of course, 1/2 is a square root, so that would be 1 over 2 square root x plus c. So sure enough, both sides are the same, so it is a solution. Both sides equal out. So we should, even if we can't solve the differential equation, we should be able, if they tell me that something's a solution, we should be able to verify that it is by this little T-chart method. Now there'd be other ways besides doing a T-chart, like somebody could just plug numbers in, and then you got to write me a paragraph about why. And I want to be very clear about why it's a solution. The only reason I like the T-chart is it's just pretty clear. It's pretty clear that yes, those two sides are equal if y is equal to this. Okay? So that's pretty much it, guys, on differential equations. Okay, now we're going to be going over the homework here. All right? So in your homework for tomorrow, and again, it's those 3 lines. There again, 2.5, 2.6, 2.7. The 2.5 section is basically this idea here. Okay, of maybe a few basic antiderivatives. There's a lot of problems that say verify that something's a solution, so you'll be doing the T-chart idea. Okay, on them. All right, let's take a look at your homework now. All right, so that's differential equation. All right, number 16. Now there's several little things in here that maybe it was easy for you, I hope so, but there are several little ideas about derivatives and antiderivatives I think are important to get across here. This one they purposely kind of I'm not trying to trick you, but really made you think about the rules, because this one would have been a lot easier if they would have made it be this. Let's just do it real quick. What's the derivative of e to the x? E to the x. Derivative of x to the fourth? 4x cubed. Derivative of 7 is 0, a constant. Well, I would say to you that this is exactly the same thing. This is e to the x. This is x raised to e. Remember, e is just a number. So it's x raised to the e. So what do? You bring the e down in front, and you drop the power by 1. And then what's e? E is just a number. What's the derivative of a number? 0. So see, there's a big difference between e and e to the x. E to the x is a function with many inputs and many outputs. E itself is just 2.718. Okay? So that's important to understand the difference. All right, and then you went to number 22, which you had to do the second derivative of that one, right? That same one, right? So now we got to do the derivative again. So derivative of e to the x, e to the x. What about this one? Yeah, I mean, what if you have 3x to the 7th, what do we do with that 3? It just hangs out there and multiplies by whatever, right? The thing you bring down. So that e is just going to hang out there. We're going to bring down the e minus 1, and we're going to drop the power one more time. And then, of course, the 0 is not even there anymore. There's nothing there, so that's it. And that's fine. You don't have to distribute the e. You could. It doesn't matter, okay, if you do that or not. That's just rearranging it, okay? If you can combine some things, that's good. But if you're just rearranging it, it's not that big a deal. Okay, and then on number 28, you had to do what? The antiderivative of that, of actually this original, right? Okay, well, again, I can't emphasize this enough. Antiderivative is not so much following the rules as it is guess and check. It's like, okay, I know the rule for derivatives is this, so I kind of do it in reverse, and then I think it might be this. Let's check it and do the derivative, see if it gives me what I started with, and if it does, I'm good. If it didn't, I'll adjust it. I mean, that's really the strategy right now for antiderivative. So e to the x, of course, is its own derivative and antiderivative, so that's easy. What about this one?
X to the e plus 1.
Yeah, we know, like, for example, if it's x to the 4th, we know it's got to be x to the 5th. It's got to be 1 higher. But, of course, then we check it and we say, well, that's not right because the derivative, that would be 5x to the 4th, not x to the 4th. So what happened to 5? Well, maybe there was a 1/5 sitting out there, right? If I'd have had a 1/5 sitting out there, because remember, a number out in front just kind of hangs out there. If I'd have had a 1/5 sitting out there, when I brought the 5 down, it would have canceled there. And then I would have ended up with x to the 4th. Well, the same thing's true here. I know this has to be 1 higher on the power. But if I do that derivative, I have an e plus 1 out in front. And I don't want an e plus 1 out there. So there must have been a 1 over e plus 1 sitting out there in front. I mean, really, that's the thought process. Okay, now I know we did talk about how if you raise the power up by 1, then you divide by that new power. That's a way to remember the power rule, too, and it works pretty well. So we could have just said raise the power up 1 to e plus 1 and then divide by e plus 1. I mean, that's essentially the same thing. But think about what you have now. If I bring the e plus 1 down, it'll cancel with that e plus 1. Just like when I bring this 5 down, it cancels with that 5. So I bring the e plus 1 down, it cancels with that e plus 1, drop it by 1, I get x to the e. All right, what's the antiderivative of e? Yeah, we said the antiderivative, we were saying that earlier, the antiderivative of 7 is 7x. The antiderivative of a number, a constant, is just that constant times x. So e is just a number, so the antiderivative of e, a number, is just e times x. E times x. Which is different, of course, than e to the x, right? So make sure you keep that straight. Okay? So that just really made you think about the rules that e is just a number, and as you'll see here in a little bit, it is pretty important, and I'll show you some examples. Okay, let's go to 18. Now 18 uses this exponential. Now remember the basic idea that a 3 to the x, the derivative is basically the same, just like e to the x. Although if it's not e to the x, we have to make this one little adjustment. We have to tack on an ln3. All right, so that's our basic rule. So on this one, we say, okay, a 2 is just a number hanging out in front, so we leave it there. The derivative of this is this. The minus 1 doesn't matter. We always leave the inside alone, right? The x minus 1 is the inside. We always leave that alone. But we have to make that adjustment where we tack on an ln3. Now, you could leave your answer just like this. Or I sometimes rearrange, bring the 2 and the ln3 together out front because they're both just numbers. And then times 3 to the x minus 1. So I kind of like having the numbers out front. Okay, the coefficients. So I'll wrap those around and write it that way. Now, why would I do that? Well, one reason I do it is because now you have to do number 24, which you have to do the derivative again. Well, I think if you have to do the derivative again, it's good to get your first derivative written in a nice, neat way that makes sense. So now I'm looking at this and I'm saying, well, that's just a number hanging out there in front. So that'll still be there. And now I have to do the derivative of that. Oh, well, we just talked about that. That's 3 to the x minus 1 and tack on another ln3. Now I'm fine if you leave it there. But you could bring that ln3 around with this ln3 and you could write 2 ln3 and that'd be all squared. The ln3 would anyway. Oops. That'd be squared, then times. Make sense? Again, keep in mind, ln3 is just a number. ln(x) is a function with many inputs for x and many different outputs, depending on what x is. But ln3 is just a number, a constant. Okay, and then you had to do number 30, which was the antiderivative of this guy here. Well, again, this is where that guess and check kind of thing comes in. Because I know when I do the antiderivative of e to the x, it's just e to the x. And I know that 3 to the x is kind of that, but there's that tack on of that ln3, so I'm going to have to deal with that. So to me, and I know the 2 just kind of hangs out there, so to me, if I was starting this, I would just start with this as my guess. Now, I know that's not going to be right, because I know it's not exactly the same, but here's where the guess and check comes in. I would just guess what, I think that's it. Well, let's check it. And what do I mean by check it? Do the derivative, right? Let's do the derivative of it. So big F, do the derivative, should be little f. So the 2 would just hang out. The 3 to the x minus 1 would be there, but I have to tack on this ln3. And I look up here and I think, oh, I don't have an ln3. Yeah, so what if I'd have had a 1 over ln3 sitting there? Now remember, that's just a number. 1 over ln3 is just a number. And the number out in front, it just kind of hangs out there. So what if there would have been a 1 over ln3 hanging out there? Then when I didn't, so if there would have been a 1 over ln3 hanging out here, then when I tacked on my ln3, those would have canceled. Just like the 1/5 that we put on with the x to the 5th. It's the same idea. So there you go. So there's your antiderivative. And of course, anytime we do it, I forgot it on the other one. Anytime we do an antiderivative, we should tack on a plus c. I probably won't take off for that if you do that in the quiz. We should tack on a plus c. And again, that's just a number. So really, technically, I probably should bring that around front. I could put that 2 and the ln3 together like that. You know, I mean, that'd be probably maybe the better way to write it, like so. But the other way up there would be okay too. All right? Number 20. What was the rule for log? 1 over the inside, right? 1 over the x, 1 over x. Now the 3 would just hang out there. Here we have 1 over x, but we also had to tack on 1 over ln2, right? With log, it was, now I know last time we were doing antiderivative, we said 1 over ln3, but that's because we were working backwards and so forth. On an exponential, you kick out an ln of the base, ln3, like we did last time. Here on a log, it's 1 over ln of the base. Now again, that's just a number. The ln2 is just a number. I keep saying this, but you're going to see here why you really have to think about that. But so I could take the 3 and the 1 over ln2, and I could put those together, and then I could write it like that. But I mean, it'd be okay to just leave it here. All right? But the reason you might want to is when you get to number 26, you have to do the derivative again. Well, to me, doing the derivative of this is a little confusing. But if I write it like this, actually I should even change one other thing. What should I do here? I should make that x to the negative 1. So what I have is this 3 over ln2, which is just a number, setting out in front of an x to the negative 1. Well, if I write it like that, then that's pretty easy, isn't it? How do I do the derivative of that? Just bring the negative 1 down in front. I'll stick it on the 3. X to the negative 2. Right? So how you write it sometimes is important in the sense that then if you have to do another derivative, how you write it, because we've got these rules for certain types of functions, so you have to make your function look like, a power. Like we did the square root over there. We did the square root, we've got to make it into a power so that we can do our power root on that. So that's 26, and then I don't think you have to do an antiderivative. Okay. So that was with exponentials and logs. Now, here's why I talk about being a number, because this gets people all the time. And if you really understand what's going on, you shouldn't trick you. Now, I'm talking about by Monday, you should really not get tricked by this. You might get tricked by it today. If f is ln x, what's f prime? Now you're scared of saying it. What's 1 over x? Isn't that the rule? Do we have to tack anything on? No, because it's ln, right? E to the x derives e to the x. Ln x derives 1 over x. When it was log, we had to tack on this. It was 1 over x, but we had to tack on a 1 over ln2. Here we would tack on a 1 over ln e, which of course ln e is just 1, so that doesn't matter. So the derivative of ln x is just 1 over x. Easy. What if f was ln 4? What's f prime? Gotcha. I get them every time. It's 0. Thank you, Ryder. ln 4 is just a number. That would be like if I said the function was 7. What's the derivative? It's 0. ln 4 is just a number, so the derivative of ln 4 is 0. ln x is a function with many different inputs and many different slopes at different places. So its derivative is 1 over x. It has different values at different x values, because ln x has different slopes at different x values. But ln 4 is just a number. If you graph ln 4, it's a horizontal line. Its slope is always 0. So understand the difference there. We got to really be careful with that, because I'll see people, same thing, e to the third. What's the derivative of e to the third? What's the derivative of e to the third? 0. E to the third is just a number. It's not e to the x, it's e to the third. It's a number. The derivative of a number is 0. What's the derivative of sine of pi? Now we're getting it. 0, because sine of pi is just a number. And the derivative of a number is 0. It's not cosine of pi, right? So I understand the difference. Derivative of a function and a number, a constant, the derivative is always just 0. All right. And I wanted to make a comment about number 35. Hopefully you've thought at least part A was pretty easy. Okay? Part A, didn't you just have to stick 40 in for t? Right? And understand why is this brought forward in here? It's because of the talk we're doing about differential equations. We talked about this important differential equation is the one about exponential growth. Well, that's what we have here. We have population with exponential growth or decay, right? If it's increasing or decreasing. Okay? So problems that involve exponential growth are important kinds of problems. So here we have a population of this town. So if this is just an algebraic equation. So you plug a 40 in for t and you get what, 200 and some thousand or 20,000 or 22,000, whatever. So you get a number. Now what does that number represent? In 2000, that's how many people were there. But then part B asks for the rate that the population is changing. See, now we get into calculus. So what do you need to do in part B? You need to do the derivative. So the derivative, the 50,000, would just hang out. This is an exponential like 3 to the x. This is just a number raised to the t, to the input variable. So that would be what? 0.98 to the t, tack on ln of 0.98. Tack on ln of the base. Now, it turns out that ln of 0.98 is negative. If you on your calculator did ln of 0.98, it's negative. What you have is p prime being negative, which means what about p? According to the chart, p prime negative, p is decreasing. This population is decreasing, and that was the question. So now you had to plug a 40 into that. So you took p prime, and you found that. It was what, 400 and something, negative 450 or something. That's people per year. They're losing people at a rate of 450 people per year at that year in 2000. Okay, because p prime's negative. See, that connects to the chart. P prime's negative, so therefore p is decreasing. Okay, so that's just kind of a problem in context a little bit there. All right, number 20. This was in the section then on the trig. I'm not going to go over all of them here. Just I picked out this one because it does have that 2 on the inside. So on number 20, we had to do the derivative. So derivative of cosine was negative sine, and we always leave the inside alone. But when you're timesing by a 2, we have to kick out a 2, and usually that ends up coming around front. You know, that's usually where we want to put our coefficients. Wouldn't have to, but we would. Now, if there's a 3 here, like if there had been a 3 in front, and then we kick out the 2, then we'd have 6, right? Then we need to put those together. When you can combine numbers, you should. If you're just rearranging them, not a big deal, but if you can combine them, you should. So there it is. Okay, and then 26 was the next derivative. So the negative 2 is just going to hang out there. What's the derivative of sine? Cosine. And you kick out a 2 again. So now you should put those together as negative 4 cosine 2x. All right, and then number 32, you were supposed to do the antiderivative of your original problem, which again is really solving a differential equation, isn't it? Because we're going from little f to big F is like going from y prime to y. Okay, so that in a sense it's solving a differential equation. And it's type 1. It's a basic antiderivative. We know we can do it because it just has x in it, which is our input variable. Okay, so what would we do? Well, again, it's kind of guess and check. You think, well, what function would make cosine be its derivative? Well, it'd have to be sine. Now, some of the other class said, well, wouldn't it be negative? Well, it's easy to confuse these because the derivative of sine is cosine. The derivative of cosine is negative sine. Now, if you try to memorize those backwards for antiderivatives, then you really get confused. I don't even do that. I just memorize the derivative formula. And then when I'm doing an antiderivative, I just think, okay, what would it have to be? And if I'm not sure, I write it down and I check it. So I think it's going to be sine 2x. And I say, well, I'll check that. Well, that'd be cosine 2x. I've already done it, actually. And then I kick out a 2. Oh, wait. I don't have a 2. So what if there'd have been a 1/2 sitting out there? If there'd have been a 1/2 sitting out here, then when I kicked out the 2, those would have canceled. So there must have been a 1/2 sitting there. And then again, somebody in their class asked, well, what if there had been a negative? Well, I'll check it. If there had been a negative, when I do the derivative of sine, that's cosine, I'd have negative cosine 2x, and I don't include it. So it must not mean anything. That's how I would know. And then don't forget, tack on a plus 2. Okay, do an antiderivative. Okay? Does that make sense? Yeah, so you got the homework right, that next group. Okay, so again, back to the things that the quiz would be about. So we've got the chart stuff and global maximum, which was really our focus the last couple of days on Monday and Tuesday. And that's a big part of it, but it involves trig functions, involves exponential functions, involves polynomial functions. All right. Derivatives and antiderivatives, we got some rules now for our derivatives, for exponentials, for logs, for trig. That's what we were just mostly going over. Okay. And then we got this new thing we talked about today on differential equation. Okay, which is kind of this. It's connected to that antiderivative notion. And then we've got this concept of what about differential equations? We don't know what the solution is. And again, the solution is the original. These two are very important right here. The definition of a differential equation is any equation that has derivatives in it. That's a differential equation. And the solution to a differential equation is the original y equation without any derivatives in it. Okay? And if we can't solve it, if we don't know what the original y equation is, they may ask us, hey, we think this is, verify that it is. And you plug that into the differential equation and show that they're the same. So those are the things that we're looking at. So the rest of this week is really about practice time on all those various things, okay? So you can look at the sheet here. So we've got right below where it says solving equations, review sheet, we've got a group of 3, that's your homework for tomorrow. So it's got some deep differential equation stuff. It's got a couple of the trig max-min kind of problems. It's got a couple of e to the x and log kind of max-min or those kind of things, okay? And then the next day we got another chunk of questions out of there that I picked out. And that'd be Friday. And then we may not even do that last group, or you'd be on your own to do that last group. Assuming we do the quiz on Monday. Okay? That's the other thing to go on. That's the plan. All right. That's all I got. You got 8 minutes. Wednesday is probably, we'll be getting into chapter 3, learning derivative rules and stuff. Nothing, no tests or anything. That's at the last part of that week. We'll be getting ready for a test on derivatives that last week before Christmas.
All right. And
Okay.
then I'll also be gone on the 17th. That's a Monday.
Okay. Kind of same thing. We may do our derivative test that